Imagine this. You're standing on the edge of a cosmic dance floor, and the dancers are galaxies, each one unique, each one telling its own story. Some are swirling like ballroom dancers, others are stretched out like limbo champions, and a few are just going with the flow, not following any particular rhythm. This is the universe we're talking about, and it's more diverse and spectacular than any dance floor you've ever seen. Stick around, because we're about to take a spin through the waltz of the cosmos, exploring spiral, elliptical, and irregular galaxies. You won't want to miss a step. Overview of galaxy types. Galaxies, the vast islands of stars, dust, and dark matter in the cosmos, come in a stunning array of shapes and sizes. Among the most common types are spiral, elliptical, and irregular galaxies, each with its unique characteristics and charm. Spiral galaxies, like our own Milky Way, are characterized by their flat, spinning disk and central bulge. They often have beautiful, pinwheel-like spiral arms that are rich in gas and dust, making them active sites of star formation. These galaxies are like cosmic dance floors, where stars are born and dance to the rhythm of gravity. In contrast, elliptical galaxies are more like cosmic orbs, with smooth, rounded shapes and a lack of distinct features. They range from nearly spherical to highly elongated and are often found in galaxy clusters. Unlike their spiral counterparts, elliptical galaxies have little gas and dust, which means they form stars at a much slower rate. They are more like quiet, serene libraries of the universe, where older, redder stars reside. The diversity between spiral and elliptical galaxies is striking, showcasing the universe's ability to create vastly different structures from the same cosmic ingredients. Irregular galaxies, as the name suggests, are the cosmic misfits. They lack the defined structure of spirals and ellipticals and often appear chaotic and disorganized. These galaxies can be the result of gravitational interactions or collisions with other galaxies, which disrupt their shape and trigger intense star formation. Some irregular galaxies are rich in gas and dust, making them vibrant hubs of stellar birth. Others are more like cosmic ghosts, with very few stars and a lot of dark matter. The diversity among irregular galaxies is perhaps the most dramatic, highlighting the dynamic and ever-changing nature of the universe. Each type of galaxy tells a unique story, contributing to the rich tapestry of the cosmos. Spiral galaxies. Basic characteristics. Spiral galaxies are among the most captivating and diverse structures in the universe. They are characterized by their distinctive shape, which includes a central bulge surrounded by a flat, rotating disk containing stars, gas, and dust. This disk is often adorned with sweeping spiral arms that radiate outwards, creating a stunning visual effect. The spiral arms are not rigid structures, but rather areas of higher density, where star formation is particularly active. This is due to the compression of interstellar gas and dust, which triggers the birth of new stars. The central bulge, on the other hand, is composed mainly of older, redder stars and resembles an elliptical galaxy in its stellar population. The diversity among spiral galaxies is remarkable. They can vary significantly in size, with diameters ranging from about 20 to over 200 light-years. The Milky Way, for instance, is a barred spiral galaxy, a subtype where the spiral arms originate from the ends of a central bar-shaped structure. This bar is thought to play a crucial role in channeling gas into the central regions, fueling star formation and potentially feeding the supermassive black hole at the galaxy's core. Other spiral galaxies may lack this bar, exhibiting a more classic, grand design spiral structure. Still, others might have patchy or flocculent spiral arms, giving them a more fragmented appearance. Spiral galaxies also exhibit a wide range of colors, reflecting their diverse stellar populations and star formation histories. Younger, more actively star-forming galaxies tend to appear bluer due to the presence of hot, young stars. In contrast, older galaxies with less ongoing star formation may appear redder. The color and brightness of a spiral galaxy can provide valuable insights into its evolutionary history and the processes driving its development. For example, a galaxy with prominent, well-defined spiral arms might be undergoing a period of intense star formation, possibly triggered by interactions with neighboring galaxies or the accretion of gas from the intergalactic medium. The dynamics of spiral galaxies are equally fascinating. The stars and gas within the disk rotate around the galactic center, but not in a simple, rigid fashion. Instead, the rotation curve, the graph of rotational velocity as a function of distance from the center, reveals complex behavior. In the inner regions, stars orbit faster, but surprisingly, the rotational velocity remains relatively constant or even increases slightly at greater distances. This phenomenon, known as flat rotation curves, provides strong evidence for the presence of dark matter. The invisible, mysterious substance exerts a gravitational influence, affecting the motion of visible matter and shaping the overall structure of the galaxy. Understanding the dynamics of spiral galaxies is crucial for unraveling the mysteries of dark matter and the evolution of galaxies themselves. Elliptical galaxies. Basic characteristics. Elliptical galaxies are among the most common types of galaxies in the universe, making up about 30% of all galaxies. They are characterized by their smooth, elliptical profiles and lack of distinct features like spiral arms. Unlike their spiral counterparts, elliptical galaxies have a more three-dimensional shape, resembling a rugby ball or an ellipsoid. This shape is a result of their formation history, which often involves mergers and collisions with other galaxies. These cosmic events can disrupt the orderly rotation of stars and gas, leading to a more chaotic and elliptical shape. In terms of stellar populations, elliptical galaxies are often home to older, redder stars. This is because the intense gravitational interactions during their formation can trigger bursts of star formation, consuming most of the available gas and dust. As a result, elliptical galaxies tend to have a more uniform, reddish hue, with fewer regions of active star formation. However, this is not always the case. Some elliptical galaxies, particularly those that have recently merged with gas-rich galaxies, can have pockets of younger, bluer stars. This diversity in stellar populations adds to the rich tapestry of elliptical galaxies. Size-wise, elliptical galaxies can vary greatly, ranging from small dwarf ellipticals to massive giants. The largest elliptical galaxies can be up to 30 times more massive than the Milky Way, with diameters spanning hundreds of thousands of light-years. Despite their size, elliptical galaxies often have a lower density of stars compared to spiral galaxies. This is because the stars in elliptical galaxies are more spread out, giving them a smoother, more diffuse appearance. However, this is not a strict rule. Some compact elliptical galaxies can have a very high density of stars, rivaling that of globular clusters. Elliptical galaxies also differ from spiral galaxies in their motion. While spiral galaxies have a well-defined rotation curve, with stars orbiting around the galactic center, elliptical galaxies exhibit more complex, chaotic motion. This is a result of their formation history, which often involves multiple mergers and interactions. As a result, the stars in elliptical galaxies can have a wide range of orbits, leading to a more random, isotropic distribution. This is one of the reasons why elliptical galaxies have a more featureless, smooth appearance. Despite this, elliptical galaxies can still have a significant amount of dark matter, which can influence the motion of stars and other visible matter. Irregular galaxies. Basic characteristics. In the vast cosmic tapestry, galaxies come in a myriad of shapes and sizes, each with its unique story to tell. Among these, irregular galaxies stand out as the cosmic rebels, defying the conventional classifications of spiral and elliptical galaxies. They lack the defined structure and symmetry that characterize their more orderly counterparts. Instead, they appear chaotic, with no discernible pattern or organization. This lack of structure is often due to gravitational interactions with other galaxies, a process that can dramatically alter their shape and composition. For instance, the Large Magellanic Cloud, a well-known irregular galaxy, exhibits a chaotic structure, with regions of intense star formation and vast clouds of gas and dust. The diversity among irregular galaxies is staggering. Some are rich in gas and dust, providing the perfect environment for vigorous star formation. Others are more quiescent, with older stellar populations and fewer signs of recent starbirth. This diversity is a testament to the dynamic and often violent history of these galaxies. For example, the Small Magellanic Cloud, another irregular galaxy, shows evidence of both active star formation and older stellar populations, indicating a complex evolutionary history. The irregular shape and varied composition of these galaxies make them fascinating subjects for astronomers seeking to understand the processes that shape the universe. Irregular galaxies also play a crucial role in the broader context of galactic evolution. Their chaotic nature often results from interactions with other galaxies, making them valuable case studies for understanding the effects of gravitational forces on galactic structures. For instance, the Antennae galaxies, a pair of colliding galaxies, are in the process of merging, creating a highly irregular and dynamic system. This interaction triggers intense star formation and reshapes the galaxy's structures, providing insights into the processes that drive galactic evolution. By studying irregular galaxies, astronomers can gain a deeper understanding of the forces that shape the cosmos and the diverse pathways that galaxies can take throughout their lifetimes. Historical discovery and classification. Galaxies, the vast islands of stars, have been a subject of fascination and study for centuries. The journey of their discovery and classification is a testament to human curiosity and the evolution of astronomical technology. Initially, galaxies were simply seen as nebulous objects in the night sky. It wasn't until the early 20th century that astronomers like Edwin Hubble began to unravel their true nature. Hubble's work led to the classification of galaxies into three main types: spiral, elliptical, and irregular. This categorization was based on their shapes and structures, observed through increasingly powerful telescopes. Spiral galaxies, with their distinctive swirling arms, are among the most recognizable. Our own Milky Way is a prime example. These galaxies are characterized by a central bulge surrounded by a flat, rotating disk. The arms are regions of intense star formation, often illuminated by young, bright stars. Elliptical galaxies, on the other hand, appear more three-dimensional and ellipsoidal. They range from nearly spherical to highly elongated shapes. Unlike spirals, elliptical galaxies lack the distinctive arms and are often composed of older, redder stars. They are typically found in galaxy clusters and are thought to form from galaxy mergers. Irregular galaxies defy the neat categories of spirals and ellipticals. They lack a defined shape and are often chaotic in appearance. This diversity is a result of gravitational interactions with other galaxies or past merger events. The Large Magellanic Cloud, a satellite galaxy of the Milky Way, is a notable example. These galaxies are rich in gas and dust, making them active sites of star formation. The classification of galaxies has evolved over time, incorporating new observations and theories. For instance, the discovery of active galactic nuclei and the role of dark matter has added layers of complexity to our understanding. The diversity among galaxies is staggering. Spiral galaxies, with their grand design and star-forming regions, contrast sharply with the smooth, featureless ellipticals. Irregular galaxies add another layer of complexity, showcasing the dynamic and often violent nature of the universe. This diversity is not just a matter of appearance, but also reflects different evolutionary paths and environments. For example, spiral galaxies are often found in less dense regions, allowing them to maintain their structure, while ellipticals are more common in dense clusters where interactions and mergers are frequent. Understanding these differences helps astronomers piece together the history and future of the cosmos. Spiral galaxies, structure and components. Spiral galaxies are among the most captivating and diverse celestial structures in the universe. They are characterized by their distinctive spiral arms that swirl outwards from a central bulge, much like the pattern of a whirlpool. These galaxies are further divided into subtypes based on the tightness of their spiral arms and the size of their central bulge, with classifications ranging from SA to SC, and even to SD for the loosest spirals. The Milky Way, our home galaxy, is a classic example of a barred spiral galaxy, a variant where a straight bar of stars cuts through the central bulge, with spiral arms emerging from either end. The structure of spiral galaxies is a testament to the dynamic interplay of gravity and motion. The central bulge is densely packed with older stars, while the spiral arms are regions of intense star formation, rich in gas and dust. This is where new stars are born, often in clusters, as the gravitational forces within the arms compress the interstellar material. The disk, which contains the spiral arms, is relatively thin compared to the bulge and can extend tens of thousands of light-years across. It's not just stars that populate these galaxies. They also contain significant amounts of dark matter, which exerts a gravitational influence but remains invisible to telescopes. Comparing spiral galaxies to their elliptical and irregular counterparts highlights the vast diversity in galactic forms. Elliptical galaxies, for instance, lack the distinct features of spiral arms and are more three-dimensional in shape, ranging from nearly spherical to highly elongated. They are often found in galaxy clusters and are composed mostly of older stars, with little ongoing star formation. In contrast, irregular galaxies defy easy classification, with chaotic shapes and a lack of defined structure. They are often the result of gravitational interactions or collisions with other galaxies, which can trigger intense bursts of star formation. Despite their differences, all three types of galaxies share common elements, such as the presence of dark matter and the gravitational forces that govern their evolution. Elliptical galaxies, structure and components. Elliptical galaxies are among the most common types of galaxies in the universe, making up about 1/3 of all observed galaxies. They are characterized by their smooth, elliptical profiles and lack of distinct structure or disk-like features. Unlike their spiral counterparts, elliptical galaxies do not have spiral arms or a central bar. Instead, they exhibit a more uniform distribution of stars, which gives them a featureless, elliptical appearance. This uniformity is a result of their formation history, which often involves mergers and interactions with other galaxies. These interactions can disrupt any existing structures, leading to a more homogeneous distribution of stars. The structure of elliptical galaxies can vary significantly, ranging from nearly spherical to highly elongated ellipsoids. This diversity is often described using a classification system that assigns a number to each galaxy based on its ellipticity. For example, an E0 galaxy is nearly circular, while an E7 galaxy is highly elongated. The size of elliptical galaxies also varies widely, with some being as small as a few thousand light-years in diameter, while others can span hundreds of thousands of light-years. Despite this diversity, all elliptical galaxies share a common feature: a central concentration of stars that gradually fades outward. Elliptical galaxies are composed primarily of older, redder stars, which indicates that they have not experienced significant star formation in billions of years. This is in stark contrast to spiral galaxies, which have ongoing star formation in their disks. The stars in elliptical galaxies are often arranged in a way that suggests they have undergone significant dynamical evolution. This can include processes like violent relaxation, where the star's orbits are randomized due to gravitational interactions. Additionally, elliptical galaxies often contain a significant amount of dark matter, which can influence their overall structure and dynamics. Another key component of elliptical galaxies is their globular cluster systems. These are dense collections of stars that orbit the galaxy as a whole. Elliptical galaxies tend to have more globular clusters than spiral galaxies, and these clusters can provide insights into the galaxy's formation and evolution. For example, the distribution and composition of globular clusters can reveal information about the galaxy's merger history. Furthermore, elliptical galaxies often contain a supermassive black hole at their center. These black holes can have a profound impact on the galaxy's structure and evolution, influencing everything from star formation to the distribution of dark matter. Irregular galaxies, structure and components. Irregular galaxies are the cosmic rebels of the galactic family, defying the structured beauty of their spiral and elliptical cousins. Unlike the well-organized spirals with their distinct arms or the smooth, featureless ellipticals, irregular galaxies are a chaotic mix of stars, gas, and dust. They lack the symmetrical, rotating disk of spiral galaxies and the uniform shape of ellipticals. Instead, they appear as amorphous blobs, often with patches of intense star formation. This diversity in structure is a testament to their dynamic and often turbulent pasts. Some irregular galaxies are rich in gas, providing the perfect environment for new stars to form, while others are more barren, with older, redder stars dominating the scene. The components of irregular galaxies are as varied as their shapes. They often contain a mix of young, hot stars and older, cooler ones. The star formation in these galaxies can be quite intense, leading to regions of ionized hydrogen gas, known as H-second regions, which glow brightly in pink and red hues. These regions are often associated with massive, young stars that have formed recently. Irregular galaxies also tend to have a higher proportion of neutral hydrogen gas compared to spirals and ellipticals. This gas is the raw material for new star formation, and its abundance explains why irregular galaxies often have so many young, massive stars. One of the most striking examples of an irregular galaxy is the Large Magellanic Cloud, LMC, a satellite galaxy of the Milky Way. The LMC is a hotbed of star formation, with numerous young star clusters and H-second regions. It also contains the Tarantula Nebula, one of the most active star-forming regions in the local group of galaxies. The LMC's irregular shape and active star formation make it a perfect example of the diversity and dynamism found in irregular galaxies. Another example is the Small Magellanic Cloud, SMC, which is even more irregular in shape and also rich in gas and young stars. These galaxies are not just chaotic, they are vibrant and full of life, constantly evolving and changing. The irregularity of these galaxies often stems from external influences. Many irregular galaxies are the result of gravitational interactions or collisions with other galaxies. These interactions can disrupt the orderly structure of a galaxy, leading to the chaotic appearance seen in irregular galaxies. For instance, the Antennae galaxies are a pair of colliding galaxies that are in the process of merging. The gravitational forces at play are pulling and stretching the galaxies, creating long, wispy tails of stars and gas. This process triggers intense star formation, adding to the irregular appearance. Such interactions highlight the dynamic nature of the universe and the constant evolution of galaxies. Distribution in the universe. In the vast cosmic tapestry, galaxies are the glittering threads that weave the universe together. Among them, spiral, elliptical, and irregular galaxies stand out as the primary types, each with its unique distribution patterns. Spiral galaxies, like our own Milky Way, are the most common, making up about 60% of the galaxies in the local universe. They are often found in low-density regions and are less common in galaxy clusters. Their distinctive structure, with a central bulge and sprawling arms, is a result of their active star formation and rotation. Elliptical galaxies, on the other hand, are more commonly found in the dense hearts of galaxy clusters. They make up about 30% of all galaxies and are characterized by their smooth, elliptical profiles and lack of discernible structure. These galaxies are often older, with most of their stars formed early in the universe's history. Their distribution is a testament to their formation history, often resulting from mergers and collisions of smaller galaxies. The diversity among elliptical galaxies is vast, ranging from small dwarf ellipticals to massive giants, showcasing the universe's penchant for variety. Irregular galaxies, the most uncommon type, make up only about 10% of galaxies. They lack a defined structure and are often chaotic in appearance. Their distribution is somewhat random, often found in the outskirts of galaxy clusters or in isolation. These galaxies are rich in gas and dust, leading to intense star formation. Their irregularity is a sign of a turbulent past, possibly due to gravitational interactions with other galaxies. The diversity among irregular galaxies is striking, with some being small and dim, while others are large and bright, highlighting the universe's endless capacity for diversity. Spiral galaxies, star formation rates. Spiral galaxies are among the most captivating structures in the universe, characterized by their distinctive swirling arms and central bulge. These galaxies are not just visually stunning. They are also dynamic stellar nurseries. Star formation rates in spiral galaxies are significantly influenced by their unique structure. The spiral arms, for instance, are regions of high density where gas and dust accumulate, leading to intense star formation. This is because the arms act as shock waves, compressing the interstellar medium and triggering the collapse of molecular clouds. The central bulge, on the other hand, is often populated by older stars and has a lower rate of star formation. In contrast, elliptical galaxies present a stark difference. They lack the spiral arms and are more spherical or ellipsoidal in shape. Star formation in these galaxies is relatively rare, as they are composed mostly of older stars and have less interstellar gas and dust. The gas that does exist is often too hot and diffused to collapse and form new stars. This makes elliptical galaxies appear more uniform and less dynamic compared to their spiral counterparts. Their star formation rates are typically much lower, contributing to their reddish hue, which is indicative of older, cooler stars. Irregular galaxies, as the name suggests, do not have a defined shape. They are often chaotic and lack the structured features of spiral or elliptical galaxies. Star formation in these galaxies can be quite vigorous, especially in regions where gas and dust are concentrated. The lack of structure means that star formation can occur more randomly and in bursts, leading to a diverse population of stars. This diversity is a hallmark of irregular galaxies, making them fascinating subjects for astronomers studying the life cycles of stars. Their irregular shapes and high star formation rates are often the result of gravitational interactions with other galaxies, which can disrupt their structure and trigger intense star-forming activity. Elliptical galaxies, star formation rates. Elliptical galaxies, with their smooth, elliptical profiles and lack of distinct features like spiral arms, present a stark contrast to their spiral counterparts. They are often found in galaxy clusters and are among the largest galaxies in the universe. Star formation rates in these galaxies are generally low, a characteristic that sets them apart from the more actively star-forming spiral and irregular galaxies. This is largely due to their composition. Elliptical galaxies are predominantly made up of older, red stars and have a significant lack of cold gas, which is the raw material for new star formation. The stars in these galaxies are often in random orbits, contributing to their smooth, featureless appearance. In comparison, spiral galaxies like the Milky Way have high rates of star formation, particularly in their spiral arms. These arms are regions of higher density, where gas and dust accumulate, leading to the formation of new stars. The presence of these arms, along with a central bulge and a disk, gives spiral galaxies their distinct appearance. Irregular galaxies, on the other hand, lack any defined structure. They are often chaotic in appearance and are typically smaller than both spiral and elliptical galaxies. Star formation rates in irregular galaxies can vary widely, but they are generally higher than those in elliptical galaxies due to their abundance of gas and dust. The diversity among these galaxy types is not just in their appearance, but also in their star formation histories. Elliptical galaxies are believed to have formed early in the universe's history, with a brief but intense period of star formation followed by a long period of inactivity. This is in contrast to spiral galaxies, which have been forming stars at a relatively steady rate over billions of years. Irregular galaxies, with their chaotic structures and varied star formation rates, are thought to be the result of gravitational interactions with other galaxies, which can trigger bursts of star formation. Understanding the star formation rates in these different galaxy types provides insights into their evolution and the broader history of the universe. For instance, the low star formation rates in elliptical galaxies suggest that they have largely evolved and are now in a state of quiescence. Meanwhile, the ongoing star formation in spiral and irregular galaxies indicates that these galaxies are still actively evolving. This diversity in star formation rates and galaxy structures underscores the complexity and richness of the universe, with each galaxy type offering a unique window into the cosmos. Irregular galaxies, star formation rates. Galaxies, the vast collections of stars, gas, dust, and dark matter, come in a variety of shapes and sizes. Among the three main types, spiral, elliptical, and irregular galaxies stand out due to their chaotic and amorphous structures. Unlike their more orderly counterparts, irregular galaxies lack a defined shape or organization. This lack of structure is often a result of gravitational interactions with other galaxies, which can disrupt their shape and trigger intense star formation. Spiral galaxies, with their distinctive arms and central bulge, and elliptical galaxies, which appear as smooth, elliptical shapes, provide a stark contrast to the chaotic nature of irregular galaxies. The diversity among these types is a testament to the dynamic and ever-changing nature of the universe. Star formation rates in irregular galaxies are notably higher than in other types. This is primarily due to the abundance of gas and dust, which are the raw materials for star formation. The gravitational interactions that often lead to their irregular shapes also compress these gases, triggering the collapse of molecular clouds and the subsequent birth of new stars. For instance, the Large Magellanic Cloud, a well-known irregular galaxy, is rich in star-forming regions. These regions, often visible as bright, blue patches, are indicative of intense star formation activity. In contrast, elliptical galaxies, which are predominantly composed of older stars, have much lower star formation rates. Spiral galaxies, while also experiencing star formation, do so in a more organized and sustained manner, primarily in their spiral arms. The diversity in star formation rates among galaxies is not just a matter of their types, but also their environments. Irregular galaxies, often found in the vicinity of other galaxies, are more likely to undergo interactions that trigger star formation. These interactions can range from close encounters to full-blown mergers. For example, the Antennae galaxies, a pair of interacting galaxies, exhibit a high rate of star formation due to their ongoing collision. This interaction has led to the formation of numerous star clusters and regions of intense star formation. In contrast, isolated galaxies, whether spiral or elliptical, may not experience the same level of star formation activity. The environment, therefore, plays a crucial role in shaping the star formation rates and overall evolution of galaxies. Understanding the star formation rates in irregular galaxies provides valuable insights into the broader processes of galaxy evolution. The high rates of star formation in these galaxies can lead to the rapid consumption of their gas reserves, potentially leading to a decline in star formation in the future. This is in stark contrast to spiral galaxies, which can sustain star formation over longer periods due to their more stable and organized structures. The study of irregular galaxies, therefore, offers a unique perspective on the dynamic and often chaotic processes that shape the universe. By comparing the star formation rates and structures of different galaxy types, astronomers can piece together a more comprehensive picture of galactic evolution. Stellar populations in spiral galaxies. Spiral galaxies, with their distinctive swirling arms and central bulge, are a common sight in the universe. They are characterized by their flat, rotating disk, which is composed of stars, gas, and dust. The arms of spiral galaxies are often sites of intense star formation, where young, hot stars are born from the collapsing clouds of gas and dust. These stars are part of what astronomers refer to as the stellar population. In spiral galaxies, there are two main types of stellar populations, the disk population and the bulge population. The disk population is typically younger and more metal-rich, while the bulge population is older and more metal-poor. This diversity in stellar populations is a result of the different environments and histories of these regions within the galaxy. The disk population of stars in spiral galaxies is often referred to as the thin disk. This population is characterized by its young age, typically less than a few billion years, and its high metallicity. The thin disk is where most of the star formation in the galaxy occurs. The gas and dust in the disk provide the raw materials for new stars, and the gravitational interactions within the spiral arms trigger the collapse of these clouds, leading to the birth of new stars. The thin disk also contains a significant amount of gas and dust, which can obscure the light from the stars behind it. This is why spiral galaxies often appear dusty and obscured in certain wavelengths of light. In contrast, the bulge population of stars in spiral galaxies is often referred to as the spheroid or bulge. This population is characterized by its older age, typically several billion years or more, and its lower metallicity. The bulge is thought to have formed early in the galaxy's history, possibly from the merger of smaller galaxies or the collapse of a giant gas cloud. The stars in the bulge are often arranged in a spherical or ellipsoidal distribution, which is why this population is sometimes referred to as the spheroid. The bulge also contains a significant amount of dark matter, which is thought to play a crucial role in the dynamics and evolution of the galaxy. The diversity in stellar populations within spiral galaxies is not only a result of their different environments, but also their different histories. For example, the thin disk is thought to have formed from the gradual accretion of gas and dust over time, while the bulge is thought to have formed more rapidly, possibly from the merger of smaller galaxies. This difference in formation history is reflected in the different ages and metallicities of the stars in these populations. Additionally, the thin disk is subject to ongoing star formation, which continually replenishes its supply of young, metal-rich stars. In contrast, the bulge is largely devoid of gas and dust, and its star formation activity has long since ceased. This is why the bulge is often referred to as a dead or passive population. Despite these differences, both populations play a crucial role in the dynamics and evolution of the galaxy. The thin disk provides the raw materials for new stars and drives the galaxy's ongoing evolution, while the bulge provides the gravitational potential well that holds the galaxy together. Together, these populations make spiral galaxies some of the most diverse and dynamic objects in the universe. Stellar populations in elliptical galaxies. Elliptical galaxies, those majestic, football-shaped giants of the cosmos, are a stark contrast to their spiral cousins. They are often found in galaxy clusters and are known for their smooth, featureless light profiles. Unlike spiral galaxies, which have a disk and bulge structure, elliptical galaxies are more three-dimensional and ellipsoidal. This shape is a direct result of their stellar populations. Elliptical galaxies are predominantly composed of older, low-mass stars. These stars are often red or yellow, giving the galaxies their characteristic reddish hue. The stars in elliptical galaxies are also typically metal-poor, meaning they have fewer heavy elements compared to stars in spiral galaxies. This is because elliptical galaxies are thought to have formed early in the universe's history, using up their gas and dust quickly, leaving little fuel for new star formation. In contrast, spiral galaxies like the Milky Way have a mix of young, hot, blue stars and older, cooler, red stars. This diversity is due to ongoing star formation, fueled by a reservoir of gas and dust. The disk of a spiral galaxy is where most of this star formation occurs, creating a stark contrast to the central bulge, which is more similar to an elliptical galaxy in its stellar population. Irregular galaxies, on the other hand, are a mix of both. They lack a defined shape and often show signs of recent star formation, indicating a diverse stellar population. This diversity is a result of their chaotic formation history, often involving collisions and mergers with other galaxies. The stellar populations in elliptical galaxies are not entirely uniform. While they are mostly composed of old stars, there is evidence of younger stars in some elliptical galaxies. This suggests that some elliptical galaxies may have experienced a second phase of star formation, possibly triggered by the accretion of smaller galaxies or the influx of gas. Additionally, the central regions of some elliptical galaxies can harbor supermassive black holes, which can have a significant impact on the surrounding stellar population. These black holes can heat up and eject gas, suppressing star formation and shaping the evolution of the galaxy. Moreover, the kinematics of stars in elliptical galaxies can vary widely. Some elliptical galaxies have boxy or disc-like shapes, indicating that their stars have organized rotational motion, similar to spiral galaxies. Others are more spherical and have random, isotropic stellar motions. This diversity in stellar kinematics is thought to be a result of the different formation histories of elliptical galaxies. Some may have formed from the collapse of a single, massive gas cloud, while others may have formed from the merger of smaller galaxies. This merger history can significantly impact the stellar population and kinematics of the resulting elliptical galaxy. Stellar populations in irregular galaxies. Irregular galaxies are a fascinating class of galaxies that defy the conventional spiral or elliptical structures. They are often chaotic in appearance, lacking the well-defined shapes of their counterparts. This irregularity is not just a matter of aesthetics. It's a reflection of their dynamic and diverse stellar populations. Unlike spiral galaxies, which have organized structures like arms and bulges, or elliptical galaxies, which are more uniform and featureless, irregular galaxies are a mix of old and young stars, interstellar dust, and gas. This diversity makes them a rich area of study for astronomers seeking to understand the complexities of galactic evolution. One of the most striking features of irregular galaxies is their abundance of young, massive stars. These stars are often found in clusters and are responsible for the intense regions of star formation that give irregular galaxies their distinctive appearance. For example, the Large Magellanic Cloud, a well-known irregular galaxy, is home to the Tarantula Nebula, one of the most active star-forming regions in the local group. This nebula is a hotbed of stellar birth, with massive stars that emit intense radiation and powerful stellar winds. The presence of these young stars contrasts sharply with the older, redder stars found in elliptical galaxies, highlighting the diversity of stellar populations within irregular galaxies. The stellar populations in irregular galaxies are not just diverse in age, but also in composition. They often contain a higher proportion of gas and dust compared to spiral or elliptical galaxies. This abundance of interstellar material provides the raw ingredients for ongoing star formation. The irregular galaxy NGC 1427A, for instance, is rich in gas and dust, leading to a high rate of star formation. This continuous star formation activity results in a population of stars that spans a wide range of ages and types, from young, hot, blue stars to older, cooler, red stars. The interplay between these different stellar populations creates a complex and dynamic environment within irregular galaxies. Moreover, irregular galaxies often exhibit signs of past interactions or mergers with other galaxies. These gravitational interactions can trigger bursts of star formation and disrupt the orderly structures seen in spiral and elliptical galaxies. For example, the Small Magellanic Cloud, another irregular galaxy, shows evidence of tidal interactions with the Milky Way. These interactions have likely contributed to its irregular shape and the diverse stellar populations observed within it. The study of irregular galaxies thus provides valuable insights into the processes that shape galactic evolution, from star formation to galactic interactions. Their chaotic appearance belies a rich tapestry of stellar activity and diversity, making them a crucial subject of astronomical research. Gas and dust content, spiral galaxies. Spiral galaxies, with their distinctive swirling arms, are a sight to behold. These arms are not rigid structures, but rather areas of higher density, often rich in gas and dust. The gas content in spiral galaxies is predominantly hydrogen, with a significant amount of helium and trace amounts of heavier elements. This interstellar medium is not uniformly distributed, but is concentrated in the spiral arms, which are sites of active star formation. The dust, primarily composed of carbon, silicon, and oxygen, is also more abundant in these regions, contributing to the galaxy's stunning appearance. The gas and dust content in spiral galaxies plays a crucial role in their evolution and appearance. The spiral arms act as density waves, compressing the gas and dust as they rotate. This compression triggers star formation, leading to the birth of new stars. The arms are thus populated with young, hot stars that emit blue light, contrasting with the older, redder stars found in the galactic bulge and halo. The diversity in star populations is a testament to the dynamic nature of spiral galaxies, where star formation is an ongoing process. Comparing spiral galaxies to their elliptical counterparts reveals stark differences. Elliptical galaxies, with their smooth, featureless appearance, lack the spiral arms and the associated gas and dust. They are predominantly composed of older stars and have little to no ongoing star formation. In contrast, the irregular galaxies, which lack a defined shape, often have a high gas and dust content, leading to intense star formation activity. This diversity among galaxy types underscores the varied processes and histories that shape the universe. The gas and dust in spiral galaxies not only fuel star formation, but also influence the galaxy's magnetic fields and radio emissions. The interstellar medium interacts with the magnetic fields, amplifying them and leading to the emission of radio waves. This phenomenon provides astronomers with valuable insights into the structure and dynamics of spiral galaxies. Moreover, the gas and dust absorb and re-emit light at various wavelengths, offering a multifaceted view of these galaxies across the electromagnetic spectrum. Thus, The gas and dust content is not just a component of spiral galaxies, but a key to understanding their complex nature. Gas and dust content. Elliptical galaxies. Elliptical galaxies, often considered the elderly members of the galactic family, present a stark contrast to their more flamboyant spiral cousins. They are characterized by their smooth, elliptical profiles and a lack of distinct features like spiral arms. This is largely due to their gas and dust content, or rather, the lack thereof. Unlike spiral galaxies, which are rich in gas and dust, elliptical galaxies are often gas-poor. This is a significant factor in their appearance and evolution. The scarcity of gas and dust means there are fewer raw materials for star formation. Consequently, elliptical galaxies are often populated by older, redder stars, giving them their characteristic golden hue. The dearth of gas and dust in elliptical galaxies is not a mere coincidence, but a result of their evolutionary history. Many elliptical galaxies are believed to have formed from the collision and merger of smaller galaxies. These violent encounters would have consumed or ejected much of the original gas and dust. Additionally, any remaining gas would have been heated and dispersed by the immense gravitational forces at play. This process is thought to be one of the reasons why elliptical galaxies are often found in galaxy clusters, where such interactions are more likely. However, it's not accurate to say that all elliptical galaxies are devoid of gas and dust. Some, particularly the smaller ones, can have a significant amount. This is often due to them accreting gas from their surroundings or stripping it from passing dwarf galaxies. The presence of gas and dust in these galaxies can lead to episodes of star formation, although these are typically short-lived and less intense than in spiral galaxies. This diversity among elliptical galaxies highlights the complexity of galactic evolution and the variety of paths that can lead to the formation of these celestial bodies. Moreover, the gas and dust content in elliptical galaxies can vary greatly from the outer regions to the core. In some cases, the core regions may harbor a significant amount of gas and dust, often as a result of mass loss from evolved stars. This can lead to the formation of young stars and even planetary nebulae. In contrast, the outer regions may be largely devoid of gas and dust, emphasizing the diverse nature of these galaxies. This variation in gas and dust content adds another layer of complexity to our understanding of elliptical galaxies and their role in the universe. Gas and dust content. Irregular galaxies. Irregular galaxies, unlike their spiral and elliptical counterparts, lack a defined structure or shape. This diversity is also reflected in their gas and dust content. They often contain a significant amount of gas and dust, which sets them apart from other galaxy types. For instance, the Large Magellanic Cloud, a well-known irregular galaxy, is rich in neutral hydrogen gas, making it a hotspot for star formation. This abundance of gas and dust is a defining characteristic, contributing to their chaotic and often beautiful appearances. In contrast, spiral galaxies like the Milky Way have a more organized distribution of gas and dust, concentrated in their spiral arms. Elliptical galaxies, on the other hand, tend to be gas-poor, with little ongoing star formation. Irregular galaxies, however, are a different story. Their gas and dust are spread out, leading to a more uniform, albeit chaotic, appearance. This diversity in gas and dust content is a testament to the varied processes that shape these galaxies. The gas and dust in irregular galaxies play a crucial role in their evolution. They fuel star formation, leading to the birth of new stars. However, the rate of star formation can vary greatly. Some irregular galaxies, like the Small Magellanic Cloud, have a relatively low rate of star formation, while others can be bursting with star-forming activity. This variability is a direct result of their gas and dust content and its distribution. Moreover, the gas and dust in irregular galaxies can also absorb and scatter light, making them appear dimmer and more diffuse. This is why they often appear as faint, amorphous blobs in the night sky. Despite this, their gas and dust content makes them fascinating subjects for astronomers. They offer a unique opportunity to study the processes that drive star formation and galaxy evolution in environments that are vastly different from those found in spiral and elliptical galaxies. Kinematics and dynamics. Spiral galaxies. Spiral galaxies are among the most visually striking and commonly studied galaxies in the universe. They are characterized by their flat, spinning disk, a central bulge, and sprawling arms that curve outward in a pinwheel pattern. These arms are not static. They are sites of intense star formation, filled with young, hot stars that make them appear blue. The dynamics of spiral galaxies are governed by the rotation of the disk, which differs from the more random movements seen in other galaxy types. Stars and gas clouds in the disk follow nearly circular orbits around the galaxy's center, creating a coherent, organized structure. This rotation is not uniform. It's differential, meaning that inner parts of the galaxy rotate faster than the outer parts. This differential rotation is crucial for understanding the formation and maintenance of the spiral arms. The kinematics of spiral galaxies, or the study of their motion, reveals much about their structure and evolution. One of the most intriguing aspects is the rotation curve, which plots the orbital velocities of visible objects as a function of their distance from the galaxy's center. In the early 20th century, astronomers expected these curves to decrease with distance, following Keplerian rotation, where outer parts move slower than inner ones. However, observations showed that rotation curves remain flat or even increase slightly, indicating that the outer regions rotate at the same speed as the inner regions. This phenomenon suggests the presence of dark matter, an invisible substance that exerts gravitational influence but does not emit light. Dark matter halos are thought to extend far beyond the visible edges of spiral galaxies, providing the additional gravitational pull needed to explain the observed rotation curves. Comparing spiral galaxies to their elliptical and irregular counterparts highlights the diversity of galactic forms and behaviors. Elliptical galaxies, for instance, are characterized by their smooth, elliptical profiles and lack of distinct features like spiral arms. Their stars move in random orbits, leading to a more spherical or elongated shape. In contrast, the ordered rotation of spiral galaxies gives them their distinctive structure. Irregular galaxies, on the other hand, lack any defined shape or structure. They often result from gravitational interactions or collisions with other galaxies, which disrupt their regular forms. These galaxies exhibit chaotic kinematics, with stars and gas moving in various directions. The diversity among these galaxy types underscores the complex processes that shape the universe, from the orderly rotation of spiral galaxies to the chaotic dynamics of irregular ones. Understanding these differences not only enriches our knowledge of galactic evolution, but also provides insights into the broader workings of the cosmos. Kinematics and dynamics. Elliptical galaxies. Elliptical galaxies, with their smooth, elliptical profiles and lack of discernible structure, present a stark contrast to the organized spiral arms of their namesakes. They are often found in galaxy clusters and are known for their older stellar populations, which contribute to their reddish hue. Kinematically, these galaxies exhibit a more random distribution of stellar velocities compared to the organized rotation seen in spiral galaxies. This is a result of their formation history, which is believed to involve mergers and interactions with other galaxies. The dynamics of elliptical galaxies are dominated by their central supermassive black holes and the overall gravitational potential of the galaxy, which is largely determined by their dark matter halos. In comparison to spiral galaxies, elliptical galaxies show a broader range of kinematic properties. While some ellipticals rotate relatively quickly, others exhibit little to no net rotation. This diversity is thought to arise from the different formation pathways these galaxies undergo. For instance, the merger of two spiral galaxies can result in a rapidly rotating elliptical galaxy, while the merger of two elliptical galaxies tends to produce a slow-rotating or non-rotating elliptical. This variation in kinematic properties is a testament to the dynamic and diverse nature of elliptical galaxies. The dynamics of elliptical galaxies are also influenced by their stellar populations. These galaxies are often populated by older, metal-poor stars, indicating that star formation in these galaxies occurred early in their history and has since ceased. This is in contrast to spiral galaxies, which continue to form stars from their gas reservoirs. The lack of ongoing star formation in elliptical galaxies means that their dynamics are not significantly perturbed by the injection of new, high-velocity stars. Instead, Their dynamics are largely governed by the gravitational interactions between their existing stars and the central supermassive black hole. Moreover, the kinematics and dynamics of elliptical galaxies can provide insights into the larger-scale structure and evolution of the universe. For example, the distribution of elliptical galaxies in clusters can reveal information about the cluster's gravitational potential and its dark matter content. Additionally, the study of elliptical galaxies can shed light on the processes driving galaxy evolution, such as galaxy mergers and the feedback from active galactic nuclei. In this way, the kinematics and dynamics of elliptical galaxies serve as a window into the broader cosmos, offering a glimpse into the complex interplay of forces that shape our universe. Kinematics and dynamics. Irregular galaxies. Irregular galaxies, unlike their spiral and elliptical counterparts, lack a defined shape or structure. They are often chaotic in appearance, with no discernible pattern or symmetry. This diversity in shape and structure is a direct consequence of their complex kinematics and dynamics. Unlike spiral galaxies, which have a well-organized rotation, or elliptical galaxies, which exhibit more random stellar motions, irregular galaxies display a mix of both. This can be attributed to their unique formation histories, often involving mergers and interactions with other galaxies. For instance, the Large Magellanic Cloud, a well-known irregular galaxy, shows signs of tidal interactions with the Milky Way, which have influenced its kinematic and dynamic properties. The kinematics of irregular galaxies are characterized by a lack of ordered rotation. Stars and gas clouds move in various directions and at different speeds, creating a dynamic and ever-changing environment. This is in stark contrast to spiral galaxies, where stars follow a more predictable, circular path around the galactic center. The dynamics of irregular galaxies are equally complex. They often have a higher proportion of gas and dust compared to stars, which can lead to intense star formation episodes. This is evident in galaxies like the Small Magellanic Cloud, where active star-forming regions are scattered throughout the galaxy, rather than being confined to a specific area. Comparing irregular galaxies to their spiral and elliptical counterparts highlights the diversity of galactic structures. Spiral galaxies, with their distinct arms and central bulge, exhibit a high degree of order and symmetry. Their kinematics are dominated by rotation, with stars and gas clouds moving in an organized manner around the galactic center. Elliptical galaxies, on the other hand, are more spherical or elliptical in shape, with stars moving in random directions. This gives them a more uniform appearance, lacking the distinct features of spiral galaxies. Irregular galaxies, however, defy these classifications. Their chaotic appearance and complex kinematics and dynamics set them apart, making them a fascinating subject of study in the field of astrophysics. The study of irregular galaxies provides valuable insights into the processes that shape galactic evolution. Their unique properties offer a glimpse into the dynamic and often violent interactions that can occur between galaxies. For example, the antennae galaxies, a pair of interacting galaxies, are in the process of merging, creating a chaotic and irregular structure. This interaction has triggered intense star formation, making the antennae galaxies a prime example of how irregular galaxies can form and evolve. By studying these galaxies, astronomers can better understand the forces that drive galactic evolution and the diverse range of structures that can emerge from these processes. Notable examples of spiral galaxies. Spiral galaxies are among the most captivating and well-known types of galaxies, characterized by their distinctive spiral arms that swirl out from a central bulge. These arms are often sites of intense star formation, filled with young, hot stars that make them appear blue. The central bulge, on the other hand, is typically populated by older, redder stars. The diversity among spiral galaxies is vast, with variations in the size, brightness, and number of spiral arms, as well as the prominence of the central bulge. One of the most notable examples of a spiral galaxy is the Milky Way, our own cosmic home. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure composed of stars. This bar influences the motion of the galaxy's spiral arms and plays a significant role in shaping the galaxy's overall structure. Another prominent example is the Andromeda Galaxy, also known as M31. Andromeda is the closest major galaxy to the Milky Way and is expected to collide with our galaxy in about 4.5 billion years. It is a large spiral galaxy with a prominent central bulge and well-defined spiral arms. The Whirlpool Galaxy, or M51, is another striking example of a spiral galaxy. It is famous for its well-defined, grand-designed spiral arms, which are the result of a gravitational interaction with a nearby companion galaxy. This interaction has also triggered intense star formation in the spiral arms, making them appear bright and blue. The Whirlpool Galaxy is often studied to understand the dynamics of spiral galaxies and the role of gravitational interactions in shaping their structure. Each of these galaxies showcases the diversity and beauty of spiral galaxies, highlighting the different forms and features that can be found within this broad category. Notable examples of elliptical galaxies. Elliptical galaxies are a fascinating class of galaxies that exhibit a smooth, elliptical profile, lacking the distinct spiral arms seen in their spiral counterparts. They are often found in galaxy clusters and are known for their older stellar populations and little to no ongoing star formation. One of the most notable examples is M87, a supergiant elliptical galaxy located in the Virgo cluster. M87 is renowned for its massive jet of energetic particles, which is powered by a supermassive black hole at its center. This galaxy is also home to several trillion stars, making it one of the most massive galaxies in the local universe. Its sheer size and influence on its surroundings make it a critical subject of study for astronomers. In contrast to the grand design of spiral galaxies, elliptical galaxies like M87 showcase a more uniform and featureless structure. This uniformity is a result of their formation history, which often involves mergers and interactions with other galaxies. Another notable example is NGC 4889, an elliptical galaxy located in the Coma Berenices constellation. NGC 4889 is one of the brightest and most massive galaxies in the Coma cluster. It hosts a supermassive black hole that is among the most massive known, with a mass estimated to be around 21 billion times that of the Sun. The sheer scale of these elliptical galaxies highlights the diversity of galactic forms and the complex processes that shape them. While spiral galaxies are often associated with active star formation and younger stellar populations, elliptical galaxies like M87 and NGC 4889 are characterized by older stars and a lack of interstellar matter. This distinction is crucial for understanding the different evolutionary paths that galaxies can take. For instance, the Milky Way, a barred spiral galaxy, is actively forming stars and has a complex structure with spiral arms and a central bar. In contrast, the smooth, featureless appearance of elliptical galaxies suggests a more quiescent evolutionary history. The study of these galaxies provides valuable insights into the processes that drive galactic evolution and the role of environment in shaping galactic morphology. The diversity of elliptical galaxies is further illustrated by their range in size and luminosity. Some, like M87, are supergiant ellipticals that dominate their clusters, while others are smaller and less luminous. This variation underscores the dynamic nature of galactic evolution and the influence of external factors such as galaxy mergers and interactions. For example, the Antennae galaxies, a pair of interacting spiral galaxies, are in the process of merging and will likely form an elliptical galaxy in the future. This transformation highlights the interconnectedness of galactic forms and the continuous evolution of the universe. Understanding these processes is key to unraveling the mysteries of the cosmos and the forces that shape it. Notable examples of irregular galaxies. Galaxies, the vast islands of stars, gas, and dust in the cosmos, come in a variety of shapes and sizes. Among the three main types, spiral, elliptical, and irregular, irregular galaxies stand out due to their chaotic and unique structures. Unlike their more orderly counterparts, irregular galaxies lack a distinct shape or organization. They are often smaller and contain a mix of older stars and young, hot stars, indicating ongoing star formation. This diversity makes them fascinating subjects for astronomers seeking to understand the complexities of galactic evolution. One of the most notable examples of an irregular galaxy is the Large Magellanic Cloud, LMC. Located about 163.0 light-years from Earth, the LMC is a satellite galaxy of the Milky Way. It is rich in gas and dust, which fuels intense star formation. The LMC is also home to the Tarantula Nebula, one of the most active star-forming regions in the local group of galaxies. Its irregular shape and dynamic nature provide valuable insights into the processes that drive galactic evolution. Another prominent example is the Small Magellanic Cloud, SMC, which is even closer to the Milky Way at approximately 200 light-years away. The SMC is smaller and less massive than the LMC, but still plays a crucial role in studying the interactions between galaxies. Irregular galaxies often result from gravitational interactions or collisions with other galaxies. These interactions can disrupt the orderly structures of spiral or elliptical galaxies, leading to the chaotic appearance of irregular galaxies. For instance, the Antennae galaxies, a pair of colliding galaxies, are in the process of merging. This collision has triggered a burst of star formation and created a complex, irregular structure. The Antennae galaxies serve as a vivid example of how galactic interactions can reshape entire systems. Similarly, the irregular galaxy NGC 1427A, located in the Fornax cluster, exhibits a highly disturbed morphology due to its interaction with the cluster's gravitational field. These examples highlight the dynamic and ever-changing nature of the universe. The diversity among irregular galaxies is staggering. Some, like the LMC and SMC, are relatively nearby and well-studied, while others are distant and more enigmatic. Irregular galaxies can vary in size, composition, and star formation rates. For example, the irregular galaxy IC10 is known for its high star formation activity, making it a prime target for studying the processes that lead to the birth of new stars. In contrast, the irregular galaxy NGC 5408 is notable for its unusual shape and the presence of a supernova remnant. These examples underscore the rich tapestry of irregular galaxies and their role in our understanding of the cosmos. Each irregular galaxy offers a unique window into the complex interplay of forces that shape the universe. Current research and future directions. Galaxies, the vast islands of stars, gas, and dark matter in the cosmos, come in a variety of shapes and sizes. Among these, spiral, elliptical, and irregular galaxies stand out as the main classifications, each with its unique characteristics and mysteries. Current research into these galaxies is revealing intricate details about their formation, evolution, and the diverse phenomena within them. For instance, studies on spiral galaxies like the Milky Way are focusing on the dynamics of their spiral arms, which are not just static structures, but regions of intense star formation and complex gravitational interactions. Astronomers are using advanced simulations to understand how these arms form and maintain their structure, with some theories suggesting they are transient features that come and go over time. Elliptical galaxies, on the other hand, present a stark contrast with their smooth, featureless appearance. Recent observations have challenged the notion that these galaxies are simple, evolved systems. High-resolution imaging has revealed that many elliptical galaxies host complex substructures, such as shells and ripples, indicating a history of mergers and interactions. Researchers are now exploring how these mergers influence the central supermassive black holes in elliptical galaxies. For example, studies of the giant elliptical galaxy M87 have shown that its black hole's activity is closely linked to the galaxy's merger history, providing insights into the coevolution of galaxies and their central black holes. Irregular galaxies, lacking the symmetry of spirals and ellipticals, are often overlooked but are crucial for understanding galaxy evolution. These galaxies are typically smaller and richer in gas, making them prime sites for star formation. Current research is uncovering the role of irregular galaxies in the early universe, where they were more common. Observations of nearby irregular galaxies, like the Large Magellanic Cloud, are helping astronomers understand the processes that drive star formation in these chaotic environments. Moreover, the study of irregular galaxies provides a window into the past, offering clues about the conditions that led to the formation of the first galaxies. Looking ahead, Future directions in galaxy research are poised to leverage next-generation telescopes and advanced computational models. The James Webb Space Telescope, with its infrared capabilities, will peer deeper into the universe, revealing the earliest galaxies and their formation mechanisms. Meanwhile, large-scale surveys like the Sloan Digital Sky Survey are cataloging millions of galaxies, providing a wealth of data to test theories of galaxy evolution. Additionally, simulations on powerful supercomputers are modeling the complex interactions between dark matter, gas, and stars, offering a more comprehensive understanding of how different galaxy types evolve. As our tools and techniques advance, the diversity of galaxies will continue to astonish and inform our understanding of the cosmos. And there you have it, folks. We've journeyed through the cosmic dance of spiral, elliptical, and irregular galaxies, each one a unique story of stars, gas, and dust, swirling and mingling in the vast expanse of the universe. Just like the diverse neighborhoods in our own cities, each galaxy type has its own character, its own tale to tell. We've seen the elegant spirals, like our own Milky Way, with their grand design and star-forming nurseries. We've marveled at the ellipticals, those ancient giants filled with older stars, and we've met the irregulars, the cosmic rebels that don't fit the mold. It's this diversity that makes our universe so fascinating, so full of wonder and discovery. As you gaze up at the night sky, remember that you're looking at a vast tapestry of galaxies, each one a world of its own. And who knows, maybe one day, we'll uncover even more types, more stories, more secrets hidden among the stars. So, keep looking up, keep wondering, and keep exploring. The universe is vast, and there's always more to learn. And hey, if you've enjoyed this journey through galaxies, stick around. In our next adventure, we'll be diving into the mysterious world of black holes. Trust me, it's a trip you won't want to miss. Until then, keep your eyes on the stars and your feet on the ground. Clear skies, everyone.